Good afternoon and welcome to the 6th session of the first edition of Técnico MasterTalks. Today's session will be dedicated to the Chemical Engineering Department. I'm Francisca, I'm a Chemical Engineering student, and I will be moderating this talk. We will have some time for your questions after the talk, and then we encourage you to know more about each of the department's masters, as well as the international opportunities, career development, and student support in the atrium right outside. I would like to first thank Professor Moisés Pinto for accepting our invite and to be here with us today. Professor Moisés is an associate of the department and has been investigating adsorbent materials and its applications for the last 15 years. He has been studying how to use these materials to separate and purify gases, store and supply them to therapeutical applications. Here at Técnico, he teaches multiple courses on different masters of this department. We will have the pleasure to hear what Professor Moisés has to say about how the development of this kind of materials can underpin key challenges we are facing nowadays, and how we as students can be a part of this.
Okay, thank you. Thank you, Francisca, for your kind introduction. So I hope I can entertain you a bit for more or less half an hour. So the purpose is for you to understand a bit what is the knowledge that we are developing in here in Técnico that is also related with the master courses, okay? So I will start by just briefly outlining what was my career until now. So my first degree was in technological chemistry, and then I had my PhD in physical chemistry already a few years ago. And then, well, I moved on and even had a startup company for developing composite media that I've been doing research during my PhD, and also other minor things that come along the way, including managing R&D activities even for the private companies. And afterwards I got a researcher position at the University of Aveiro, and a few years after I got a position here at Técnico, yes, in 2015, and I've been here since then and already participating in different positions, the executive committee, also, for instance, in the Portuguese Chemical Society, in the Pedagogical Council, and more recently at President of Serena. So now I'm associate professor, and as Francisca already mentioned, I'm lecturing in and I would say sufficiently large number of curricular units in different masters, okay? So I'm going to talk a little bit about the masters also. So moving to the department, so the Chemical Engineering Department is one of the founding departments of Técnico. So it's, so you see in here the picture of the old facilities at the Instituto Industrial e Comercial de Lisboa. So, and the first course was Engenharia Química Industrial. So we have quite a long track record here in Técnico, yes, and we are currently about 60 permanent faculty members. I think I'm over here. Okay, so it's very important for us to be involved, of course, in teaching, but also in dissemination activities, in our outreach activities, for the society, mainly reaching students, young people that may be interested in our area of development. So these are some of the activities that we have been developing, and some pictures, and I think that some of you already participated on these activities that happened already for quite a long years. Okay, so the master degrees that the department is deeply involved are these 5 master courses. We have in these 5 masters around 320 students. So you see here we have a chemical engineering master, then a master in molecular sciences and engineering, a master in environmental engineering, a master also in materials engineering, and last, master in pharmaceutical engineering. Some of these masters are, of course, together, let's say, lectured with colleagues from other departments, okay? So, for instance, the master in chemical engineering, you see here the specialization area. So we have product engineering, process and system engineering, sustainability and energetic transition, catalysis and polymers. And this gives the possibility of the master students to get knowledge to tackle with very relevant nowadays problems that you see in here. So these, of course, are problems that are interesting for different areas of the society, not just, let's say, chemical engineering factories, let's say, but also consulting, research, teaching, as you see in here. So also these more information about this course can also be found afterwards. The other course that I already mentioned is the Master in Molecular Sciences and Engineering. So the study areas are moving between molecular simulation, molecular design, analytical methods, and structure analysis. And this should give the students the tools to also move on these fields that you see in here, even from small molecules to polymers, nanomaterials, chemical and biological functions, sustainability. This is always an issue nowadays, as you know. And of course, one important thing to consider is where you can afterwards get positions. Okay, what are the main areas that are contracting our students? Yes, so you see in here, doing from research until environment, materials, cosmetics. So as you see in all these masters, you have a broad scope of possibilities afterwards. The master in environmental engineering is giving competences for the students in these areas, as you see in here: management of natural resources, prevention and treatment of waste and effluents, environmental modeling, impact assessment, and materials in circular economy. And as you see in here, this is also gives the students the possibility afterwards to tackle with these challenges that are, as you know, very relevant nowadays. This is, I would say, one of the biggest challenges nowadays is, in fact, related to environmental sustainability. And if you look at the areas where the students that finish the course will usually go to get positions, you see in here, from industry, but also, in this case, state agencies, consulting, central and regional administration. So it's also a wide area of positions that you can get. The master in materials engineering, there are two main specializations. One that is related with materials technology. So we have different types of materials that you can get specialized with, and also depending on the function, what is what you are going to do with the materials. Okay, for instance, nanomaterials, functional materials, biomaterials, and this you will be possible to be applied for different areas, as you see in here: biomedical application, industrial materials, in the field of energy, and many more. I will also talk quite a lot, I would say, about materials. This is an area where I'm also doing research. So students that usually finish the course successful can find positions in these areas, as you see in here. From, of course, development of materials, but also until consulting and control and so on. So this is also a wide area of possibilities for the students that finish this course. And the last one is the Master in Pharmaceutical Engineering. This is a joint master with the Faculty of Pharmacy, also from the University of Lisbon. And the specialization areas you see in here. So it's development of new processes to produce drugs, the production and process management, the quality control of the products, also life cycle management of the life cycle of the products and of APIs. And the graduates that finish the masters usually found positions in these areas, as you see in here. So I'm just very briefly summarizing what is the offer of the department in terms of masters. As you see, there is a significant wide range, not only in competences but also in the positions that you can get after. Okay, of course that these are quite a lot related to each other. Okay, these are not, how to say, hard borders between these, and I think that I will show afterwards that I'm also, I would say, one example of this. Okay, the research inside the department is organized in these 4 research centers. Most of researchers and faculty members are in the 2 ones that you see in here, in CQE and Serena. Well, distribution is in here, is difficult to see. And this is where we are developing most of our research. Sometimes there is not sufficient visibility of the research center to students, yes, because probably you don't have sufficient opportunities to understand what is going on in this, I would say, parallel reality inside your school, okay? So I will have now the opportunity to talk a little bit about some of my research topics. I will try to be, how to say, as simple as possible, but nevertheless I will try to show what some of recent colleagues of yours have also contributed to the work that I'm going to present. Okay, this can give you some ideas, or at least help you to decide what you want to choose. Okay, so I'm going to talk about capturing of CO2. This is, I would say, a more or less hot topic, and nevertheless I'm doing this for, I would say, more than 15 years already. Also, the development of nanoporous carriers to deliver nitric oxide. This is more related to health, yes. And you see here the removal also of volatile organic compounds, and this is related to cultural heritage protection. So you will see that these topics are moving, the different topics are moving across, in fact, all these fields of these masters. Some of them are more related to some of the masters that I talk, so I'll try to highlight a little bit. And these are also related with these sustainable development goals. I don't know if you already have learned about them. These goals are challenges for all of us to have a sustainable life on Earth, okay? So I will start by talking about capturing CO2 with advanced porous materials. So you see here a picture, what is one example of a porous material. You see this is 100 nanometers, so we are talking about pores of just a few nanometers. So we are more or less of the size of the molecules. This is what I call adsorbent materials. So molecules like to go inside in here due to the forces that attract them to the surface, okay? Of course that the adsorbents can be applied to capture CO2, and one of typical, I would say, examples is when you want to capture CO2 from a fuel, flue gas from a fuel that is burning. So you would want to capture the CO2. Another example that you may know or not, because it's not so well disseminated, is when we have, for instance, biogas that is produced. We have methane-rich gases, and we want to remove CO2 from these streams to, of course, use the methane, okay? This can be from landfill, biogas, and so on. So materials can be used for this. The regeneration of the adsorbent bed is always a possibility, so we only need to consider this. I mean, it's absorbing CO2, but afterwards you want to regenerate the material, so you are separating the two gases. And of course, the efficiency of these processes is highly dependent on the nature of the materials that you use, okay? So we need to develop these materials, and there is quite a lot of development nowadays going on related to this, okay? I will just show one example from what I've been doing, and I will not show all types of materials. So for instance, one material that we have been exploring for quite a long time is based on natural clays. These clays have structures in layers, and we have some cations inside, and we can exchange by zirconium oxides or zirconium or aluminum oxides, and we have this kind of pillars. So it's like a structure, like a building, okay? You have some layers and some pillars. And we have these spaces, and molecules can be absorbed. So in here you see the amount that we can get inside as function of pressure. So if we compress, some gases go inside. What is interesting to look at is that, okay, nitrogen is in here, but CO2 is over here. So the molecules are not going inside in the same amounts. So we can use this for our own benefit, okay? So we can calculate what we call selectivities. It gives you an idea of the ratio between what is inside of the two molecules, and you see you have here some high values for these mixtures. And what we can do afterwards is to use, process, to develop processes where we can compress and decompress the gas inside, and we can use some simulation tools that you see in here, and try to understand if we can separate the gases and of course get some values for the energy consumption, purity, and so on. We can even develop more complex processes like you see in here, where the gases are passing from one column to the other. We are trying to compensate for the pressure, to be more efficient, and so on. And then in the end, actually what we want is to have values more or less like this. Well, this was done with together with a company, Cecil, you may know the company. And for instance, in here you see what is the capital, what is the investment, what is the CO2 that is emitted per year, and what you are removing, and in the end, what are the costs. So this is something that is related with materials engineering, as you have seen, is also related with chemical engineering, process engineering, and well, these are two master students. João is now, I think, at Galp, and Carolina is at Shell in the Netherlands. A few years ago, they were working on this project. And as you can see in here, these are the two, examples against other benchmarks. And nowadays, well, we have recently José that was working as with a grant in here. And here we see a researcher from my group, Tanya, that is doing a scale up with this. And you see in here what we call the breakthrough curves. You see we are putting a mixture, but nitrogen is going out of the column first. So if I can put the nitrogen from one side and then switch the valve for the other side, I can separate the two gases, okay? So this is a mixture, but at the outlet you can separate, okay? So what to do with the CO2? This is always a question. I put here this is the Roman god for the end and for the beginnings. This is the Janus god, so they put this in the doorways. This is the end, yes, but no for instance, for plants, this is the beginning. So if we get inspiration from plants, this is the starting of something. They are collecting CO2 to build up molecules, and we can also try to do this. And there are many people now developing process to convert CO2 to other stuff, okay? This is at the core. So what we are teaching to students is at the core of the challenges of the society nowadays. So we can transform this to methane, for instance, using, of course, renewable energy. And we can also, for instance, do polymers. You can do the synthesis of polymers with CO2. So another example that I'm going to talk about is related with nitric oxide. I already talked a little bit about this. Is more related with health. So nitric oxide it's a very toxic gas, but is produced inside our bodies to control many biological functions in the body. And we have been trying to release it slowly and control in some parts of the body for wound healing, for instance. Well, what is the problem with classical donors? So if we look at the literature, you already have molecules like these ones that I put in here that degrade and they produce NO. But the problem is that these can spread all over the body and they are toxic. So actually the strategy is, for instance, if we load the nitric oxide inside the pores and then we put the material just in the wound that you want to treat, this can do the job and not spreading the toxic molecules across the body. So this is more related with materials, also molecular sciences, and also with pharmaceutical applications. Okay, so we need to develop materials because, for instance, we have a problem of fast release in media. Usually these materials are not releasing slowly. They have low stability. Some of these are leaching metals, and we also have toxicities, and they are difficult to handle if they are powder. So we can address some of these problems by tuning the material. Other ones are a little bit less straightforward, but nevertheless we can always try to solve. I will show after. So the materials, we can look at them as being a kind of Lego. So for instance, if instead of using this small molecule here that are bridging these parts that are zirconium oxide clusters, so instead of using this small molecule, if I use a little bit bigger molecule, I can tune the size of the pore. So nowadays the technology is already at the state where we can actually tune the size of the pores. We can tune the chemical environment inside the pores. This can be interesting because we can do quite a lot of different materials and with different environments and binding NO in different ways. I'm not going, of course, to give you here in very insightful, but just to give you an idea that we can in fact tune to, for instance, in this case, NO is reacting with a OH group and having these bridge nitrite groups. And in some of these cases, well, this is just a small movie to give you a 3D perspective of the materials. So in some of these cases, so NO should bind more or less in here. In these cases, we can afterwards, if the material is slowly releasing the nitric oxide, we can tune the cellular functions. We can put these materials in contact with cells, and then we can trigger the cell migration, which is one of the natural effects that NO does in the body, is to close the wounds by migrating the cells. Okay, and we can see in here an increase about 8%. And we can also tune another thing, which is the respiration of the cells. So if we put NO in contact with the cells, we stop the mitochondrial respiration, and you see here a correlation between the NO release and the mitochondrial consumption respiration. So when NO is being released, it stops, and then NO is not being released anymore, it goes back again. So we are not killing the cells, we are just tuning the cellular functions, okay? And as I said, well, instead of powders, we can even do some films, some composites, and so on. So this is a student, a master's student in chemical engineering that is now working in this topic, and this is Rosanna that got a PhD in chemistry a few years ago. She's now a researcher in France, and is coming back because she got a 6 years contract now in Portugal. Okay, now changing again for another topic, and this will be my last one, is more related with cultural heritage. So may seem a little bit strange why volatile organic compounds are related with conservation of cultural heritage. So I will try to contextualize in here. We have, of course, volatile organic compounds as a general problem, yes, so molecules that are inside the buildings and so on. And we have even the problem of sick building syndrome, and we have regulations and so on. And we have several methods to try to remove these molecules, but some of them are not very suitable to be used in cultural heritage conservation. As you see, thermal composition, oxidation, and so on. It means that you need to heat up or introduce oxidative or wherever, and then people from the museums and galleries and so on, they don't want to add more things over there. They just want to remove CO2. The VOCs. So for the VOCs, adsorption can be something interesting because you put the material, the VOC goes inside, and then you remove the material with the molecules that you want to capture inside. So the problem of acetic acid is particularly complex because acetic acid is a very polar molecule, yes, and water is also. So to have a material that can capture one but leaves the other, it's a challenge, okay? Because they are, how to say, similar, okay? So what we have done is actually to develop materials that are good for this, and they can be interesting for solving problems related with cultural heritage. As you can see in here, we have the problems in film archives. These films, historical films, have been for decades made of cellulose acetate, and cellulose acetate, as the name says, we have acetic acid being released from the acetate groups, and what happens is that the acetic acid catalyzes even more the degradation, so it accelerates. The same type of polymer can also be found in many different modern art pieces, because modern artists are using almost any type of material for building their pieces. But the problem is for the curators and conservators in museums to have these pieces for years. I'm talking about 100, 200, 300 years, because this is the timeline for the museums for conservation. This is challenging. And you've seen here, for instance, this piece was in the Tate Museum, and it was completely degraded. They asked the artist to make a new one. He did a new one, and it's already degrading again. Okay, it's difficult. This is what they call the vinegar syndrome, because it smells. It starts to degrade and it smells vinegar. So I'm not going to discuss much about the strategies that we use. Nevertheless, just a very simple idea that we have also used to test is, for instance, if the material is good, then when we put acetic acid here inside a chamber, a small chamber where you have moisture and just a very, micromoles of acetic acid, just a very little bit of acetic acid, we should monitor and see if acetic acid is released. So you see here, it goes up the concentration, and then the adsorbent starts to do the job, and then it disappears. So this is what you want, something that when it is in contact with air, with acetic acid, it can remove this vapor. So we did quite a lot of experiments. I'm not going to show everything. I would say that one interesting thing is to also to use now computational tools to understand a bit what is happening at molecular level. So you see here two examples. In this case, we are doing the modeling as, classical objects, yes. So in this case, this is what we call classical molecular modeling. And in this case, it's more based in quantum mechanical methods. So in here, we are considering the electrons in the molecules, okay? So these computational tools give us insight. So in here you can even have an idea of the energy of the interaction. And you can compare this with experimental data and see if the models are representing well what you want. So this is very interesting, but in the end we want to use the material inside the box where you have films, okay, the reels, And then we started to talk about with people from the archives about, oh, well, what are the amounts that we need to put? Yes, but I mean, what in this case, these metal organic frameworks, what we should put inside? So it depends on the acetic acid that is emitted. Yes, it makes sense. You put more if you have more emission. But they didn't know. This was actually, they sense, but they didn't know how much is going to be emitted. So, and how fast are the films degrading? How fast is that this VOC is being released for the cans? They also didn't know about. So all the degradation state affects the degradation rate, because we already know that this is autocatalytic. So more degraded, it means that it is even faster. So they didn't know also about. So also the temperature and accumulation and so on. So many questions that they didn't know. So we had to go to the basic, how to say, fundamental stuff and try to calculate from, how to say, first principles, the kinetic constants, and then also the water from the literature equations to model what was the water accumulation, and also did the mass balance equations inside the film cans, and then we use some machine learnings to correct this, how to say, theoretical model for the real films. So we treat, I would say, the cans a little bit like a small reactor where we put our adsorbents. And then one interesting thing, okay, these are fancy calculations, but how this compares with what you have. So we could calculate, for instance, you see in here time year, so the timeline is up to 100 years, and we can see, for instance, in this case, where the pink and the blue is when you are freezing the reel. This is one classical option, we just put in the freezer, yes, but the power consumption is very high because you are talking about storing movies in the freezer for decades. And the other option, okay, it's, for instance, we just have 18 degrees and we put more or less normal temperature and we put a small amount of the adsorbent. And you see that the result is the same, okay? And we can see a little bit why, because we are removing, you see here the concentration of acetic acid, and we are removing the VOC from the air surrounding. So we are stopping one of the degradation channels, the acid catalyzed degradation channel. So in the end, we assembled all this, and they did the tests at the archives, and the comparison was very good, okay? So in the end, it works. So, well, this Abir is a researcher, and Katia is a researcher now at Iberian Nanotechnology Laboratory. They have been working in this project, and Inês was a master's student in chemical engineering, and she got the PhD in materials chemistry in France, and she's now working, I think, in Air Liquide in France, using these tools that she learned. Okay, so I'm about to finish, and remembering you about the information of the masters, I think that I was a little bit able to, how to say, to give you a little bit of the tools that we can use in different aspects of problems that are coming from all these masters, okay? So I encourage you to get more information, and of course I will be more than happy to answer to the questions you have, okay? Thank you.
So thank you once again for giving this informative and exciting talk. I'd like to start by asking if there are any questions in the audience. So I would like to first ask you a question. What is your advice for all of us that are starting to think about the masters? What can we do as choosing a thesis theme?
Well, I think it's, if you want to choose a thesis topic, I think it could be good for you to understand from your perspective today, what you would like to do in the future, because the master thesis can be, how to say, a door for this. For instance, in the case of Inês, that I just talked a few minutes ago, she wanted, the master dissertation was already done in this topic, yes, developing some materials for this, and she wanted to work in this field, yes. I think you need to really understand from all the possible areas, because the chemical engineering department is giving these masters that have a wide range of skills, give you a wide range of skills. You can in the future work in many different types of institutions and you need to choose. So I don't have a very simple question for this, because, and also don't be, how to say, very stressed if you think that you are not choosing wisely, because you are still young, you can change, okay? So if you choose something that after a few years you want to change topic, also the skills you get from these masters also allow you to change. Yes, this is good, because if you are just very, how to say, expert in a very narrow field, this will be more complicated, okay? I don't know if I gave a simple answer. I think not.
I would like to again encourage you to, if you have any questions, you can do them now.
So thank you so much, Moisés, for your master talk. I think you give a good overview about the department and masters that we can offer to students, and also a very nice overview about your research and your group. My question, or if you can elaborate a little bit of your experience on having students with a not complete master, I mean with the first cycle, how to compare the performance of this student with the students with masters, or even more in the PhD students?
Yeah. Well, I think my opinion is that students that finished first degree, okay, just bachelor, they have, of course, skills that can be interesting for these fields, but it will be much more difficult to get sufficient insight and to start, how to say, developing more advanced work, okay? For instance, in the first case that I gave about development of materials, and then you need to use the materials in the process, and then you need to calculate, to master all these skills, you need to get a master, okay? I think this is summarizing. Because we are going beyond in some of these applications, and my feeling is also that also the market wants students, when they are hiring people, they want skilled people, but that goes beyond what is just simple approaches, yes? Even because I think, and we have been discussing this also among ourselves in the faculty staff, this is, I would say, challenging times also for young students and young professionals, because you have more and more intelligent tools, and you need also to compete with these. You are now starting to compete, or machines are starting to compete with us, okay? So if we are just giving, how to say, very simple standard answers, we are not giving, how to say, our value is not so high compared with, okay? And I think it's more and more important to young students to think about that they are investing on themselves, yes? This is an investment for life, I would say.
So, thank you, Professor. I would like to then give the word to the other teacher.
Hello, thank you very much for Tá bem, okay. Better now? Okay, so as far as I could understand, you had porous materials, you were trapping molecules inside the pores.
Yeah.
And my question is, can you reuse them? So this
Yeah.
means, can you clean those materials and then
Yes.
reuse them again? Thinking about sustainability, this is...
Of course. When the first example that I gave, it's a cyclic process. We have a column, we are pressurizing CO2 and methane, or CO2 and nitrogen, and then we regenerate by lowering the pressure. So, in the end of the cycle, you have a clean column. But of course, first you get out the molecule that is less adsorbed, and afterwards you continue to decrease the pressure and you get out the molecule that is more strongly adsorbed. This is what we call, for instance, pressure swing adsorption. You can also use temperature, because adsorption, well, I don't want to give a very complicated lecture for students, but adsorption in terms of thermodynamics, yes, it releases heat. So if we heat up the material with something inside, we are pushing out the molecules. So we can clean also the materials with temperature. And in this case, we talk about a different class of processes, which is temperature swing adsorption. So, and these are in the industry already, so we are not inventing anything. The challenge here is to have materials that can do this efficiently, because if they bind the CO2, for instance, very strongly, you use them, but then you need to spend quite a lot of energy to regenerate them. So there is a balance between what we call selectivity and other, how to say, parameters, okay? Because sometimes people just worry much about selectivity. Yeah, but we don't want to use the material just once, okay? This is not the purpose. So this is cyclic adsorption, yeah? In other cases, for instance, for, how to say, biomedical applications, most probably doesn't make sense to regenerate the material, because we are talking about devices that you put on the wound and you are not going to reuse them also because of other issues, not the material, but it was in contact with a certain person and then contamination, biological and so on and so on. But in this case, we are talking about very, very small amounts. Yeah? But for large scale applications, materials always need to be reusable, several thousand times.
Again, I would like to ask if there's any question from the audience. Yes, please.
Hi. Hi, thank you for the presentation. I have a question about a more broad question about the masters. I've noticed that in each of the projects you talk about a certain process that exists between finding, testing hypothesis, the typical empirical method.
Mm-hmm.
But it always, or almost always, starts with a problem that needs to be solved, and then you start microscopically. So you start with molecules, and then you tend to ascend to reactors and industry.
Yeah.
So how would you describe, in terms of timeline, would be the process of trying to solve a problem industrially wise?
Yes. I think nowadays, and this is something that is part of the field of chemical engineering, chemistry, materials engineering, pharmaceutical engineering, and so on. So the knowledge we have nowadays allow us to think on the problem starting from first principles. For instance, the example that I gave, I was talking with people, and this was a very tough problem for us. We had the materials, they absorb VOCs quite well, yeah, now okay, so what is the amount that we put inside? I can do some basic engineering calculation, but you need to say to me what is the amount of acetic acid. They didn't know. So, and sometimes to answer very simple questions, you need to follow this complicated process. If we understand, for instance, in the literature, there was already some work related with the degradation of cellulose acetate. And our first idea, okay, we go there and get the kinetic constants for this. There were not. You could not find them. So you see, we could go for these, how to say, molecular modeling tools to calculate. For instance, this is what we have done. And this is something that I would say 20 years ago was a little bit more complicated. Nowadays, you can use these strategies as tools. So you can start by thinking from molecules until full-scale processes. But you need to consider one thing, is that the detail of the models starts to be a little bit, for instance, the last step that I gave over there was, okay, up to a certain point the model works perfectly, but this is for pure polymers. But the films that you have in the cans have quite a lot of additives, okay? I'm not going to talk here, but quite a lot of things that they add to the polymer, and this influences the degradation. But even now you have tools like machine learning algorithms and so on, so if you have statistical data, you can also learn from there, and what we have done is, okay, this is the basic fundamental model, and we can correct. So if the model was from a certain decade and from a certain supplier, we apply some corrective factors, and we have what is the expected degradation kinetics and so on. So this type of strategies can nowadays be used. But in this case, it was for this degradation of films. But you can also use these things for large process, yes, in chemical engineering, for instance. Yes, you can start by simple models, and then you can use these corrective models, let's say.
So thank you for your answer, Professor. Again, does anyone want to ask any questions? Maybe I would ask another one. One of the growing concerns for the cultural heritage is maybe statues and things and heritage that's outside and
Yes.
being degraded because of acidic rains. Have you ever wondered what could be a solution to preserve those kind of art?
In these cases, from what I know, there is quite a lot of developments in the last years to have this type of coatings that can be applied. And of course, we are talking about art pieces, and people from the conservation field, I started to know them in the recent years. They don't like to put new things in contact with old things. It's like you need to demonstrate that these are innocuous. And one of the things that usually they like is you need to demonstrate that in the future, if you want, you can remove it. So it's a little bit tricky, okay? But there are people now proposing some types of polymer coatings and so on to protect stones, to protect metals and so on. And this is, I would say, something that is very important for young professionals to understand, is that, okay, you have your skills and you have all your knowledge and so on, and then you have one idea, a very brilliant one, how to solve this problem, and then you go and talk with the people from that field, and they raise you a million questions that you didn't thought about it, and some of them are not obvious, okay? For instance, in the case of museums and galleries and so on, there are questions. I will not try to spend too much time in here. There are questions that, for me, I was not thinking on this. I need to be honest. I was not thinking, because I was thinking on how to solve the problem from an engineering, chemical, materials, and so on perspective. And in the end, they raise you quite a lot of questions that are related with social sciences and then historical and museological issues. And then, oh, okay. So if I want really to solve the problem, I need to understand them. And this is, I think, why it's very important to have these boundaries between different domains in science, yes? And I think students now have the opportunity also to learn not just engineering stuff, let's say, and I think this is important also.
Again, does anyone want to ask any questions? Some of the faculty, maybe? Okay, so maybe one last question. How can sustainability be included in this research for materials and...
Well, I would say that nowadays sustainability is, I would say, crossing all domains, yes? In the case, for instance, where in development of new adsorbents and so on, this is a very important issue, and the choice of this choice of natural clays that I was putting here, it's also because of this. So this is something that already exists in nature, so we can just change a little bit the material, introducing some permanent porosity and so on, and then in the end you have a material that is capable of absorbing CO2, but it's still a clay. So in the end, when the material is not working anymore, it will not pose significant danger to the environment. Okay? On the contrary, there are other materials, for instance, like the ones that I've shown, one type of materials, for instance, the metal organic frameworks. We have some metals over there. So it depends if the metal is aluminum, maybe not a big issue. But if the metal is chromium, yes, then the story is different. It's very difficult to have nowadays, even chemical industry is very sensitive to this. You cannot convince a company to start, how to say, producing or scaling up something that is not crystal clear to them, that they will not have issues, environmental issues or health issues. And I don't know if you know about the fluorinated compounds and so on that people are now complaining about. So if, for instance, if you go now for a company and start talking about producing new compounds with fluorine, they'll say immediately, no. Yeah. You need to convince them. Maybe they will, but it's just, well, coming back to your question, sustainability is always, how to say, now a baseline for all type of research and development, I would say.
Thank you. So this concludes our master talk. I would like to thank Professor Moisés again. And I would just like to encourage you again to go outside to the atrium. We have the coordinators of these masters here, then you can ask questions. This doesn't happen very often, so seize this opportunity. And I would like to also remember and warn you that the inscriptions for the next Master Talk are open. It's going to be for the Department of Nuclear Sciences and Engineering, and you can already sign up for that Master Talk. Thank you all for coming, and I hope you seize this opportunity to talk about Masters and Professor Moisés' research. Thank you.
Thank you.